So we are still looking at graphs. Today our focus is going to be in particular on absolute values and their transformations. We're going to look at how the slope affects an absolute value. It's also important to know how and where to plot points. So we're going to look at plotting each of these points, making sure each one is also labeled. So when we are labeling our points, you want to put like A, you want to put B, you want to make sure you have the letter next to them indicating which point it represents. The points go X, comma, Y. So again, any point on the x-axis is the x-intercept. Any point on a y-axis is a y-intercept. So we are still going to take into account all of those. The reason we focus and talk about plotting points is because as we look at absolute values, we are going to talk about how to find their vertex. The vertex is the starting point of the absolute value. So our goal is to be able to graph absolute values at particular points, allowing them to be transformed from their parent function. Yesterday we talked about parent functions, and the absolute value parent function is the absolute value of x. The function f of x is what we will refer to as an absolute value function. The highest or lowest point on the graph of an absolute value function is called its vertex. The vertex is going to act as the min or the max of that graph. It's going to act as the min or the max of that graph. When we talk about domain and range, the absolute value is going to be a part of our domain or range. So when we talk about domain and range, the absolute value is going to be a big part of our range. And then the axis of symmetry of a graph of a function is a vertical line that divides the graph into two mirror images. So the axis of symmetry is the line that divides the graph into two mirror images. So yesterday we talked about the parent absolute value function. We talked about it being the V-shaped curve. I implied that an absolute value function could be written as a piecewise. I implied that an absolute value function can be written as a piecewise. So it is equal to negative, the negative x for x values less than 0. It is equal to 0 when x is 0. It is equal to x when x is greater than 0. That's because an absolute value is really two lines meeting at a point. Since we don't know which line includes 0, 0 is its own individual point. So we talked in piecewise about something being its own point. So 0 at x equals 0 is its own. Okay, so the graph, I gave you space to graph it on that front page. Nope, still on the front page. Still on the front page. So you have a blank graph next to all the vocab. So the absolute value function f of x is the V-shaped curve that goes through 0, 0. Its vertex is at 0, 0. We just talked about it being a piecewise graph. X values greater than 0 have a positive slope of 1. So that's the right side of the graph going up towards infinity. The left side has a negative slope for x values less than 0. The domain of an absolute value is always all reals. The domain of an absolute value is always all reals. The range is y greater than or equal to 0. The range is y greater than or equal to 0. You're written on this page, it's not a big deal. I just wanted you to figure it out. So yesterday we started to introduce transformations. Today we're going to focus solely on transformations of absolute values. We're going to focus solely on absolute value transformations, where all the rules we used yesterday still apply. So all the rules we learned yesterday still apply. So we have y equals negative a absolute value of x minus h plus k. Everything is a part of the parent function except for the negative. The negative is a reflection. So if you have a negative in front of your absolute value function, then the graph will be a reflection across the x-axis. So that is the first type of transformation. So a negative a will reflect the graph across x. We saw that yesterday. An a value is going to be our stretch or compress. The a value is going to be the stretching or compressing. H is horizontal translations. It is always on the opposite direction of what you see. So they are our horizontal translations. They are in the opposite of what you see because the formula itself is x minus. So again, the h you're seeing is a positive h because it's a minus. Or if you see a negative h, that negative is part of the equation, not the translation. The k value are our vertical translations. That is your movement up or down. The k value is your vertical translations. That is your movement up or down. And then I have like a little side note down there that's hard to see. And it says, remember that h comma k is your vertex. So the vertex is going to be the tip or the max or min the opposite value graph. So what we can do is actually treat our opposite value graphs like piecewise and apply our slopes and know that the transformations are where it moves to. When the A value is positive, your graph will open up. When the A value is negative, your graph will open down. So that negative A is that reflection across X. A negative inside the absolute value is a reflection across Y. It is less easily visible inside an absolute value. And then yesterday we talked about stretching and compressing. When you talk about something being stretched or compressed, it is its absolute value. When you talk about being stretched or compressed, we're talking about the absolute value of A. Graphs will be stretched if their A value is greater than 1. Graphs will be stretched if their A value is greater than 1. If an absolute value is stretched, it will look narrow. If an absolute value is stretched, it will look narrow. Because the slope is steeper, it is rising quicker, looking narrow. If the graph is compressed, then it will appear wider or shrunk. If a graph is compressed, it will appear wider and shrunk. The A value is outside the absolute value. So we're talking about this A. This is only for A values outside the absolute value. So then now what we're going to do is identify our vertex, identify the A and what it does to our graph. So in this case, the graph is not shifted left or right or up and down. So my vertex remains at the origin. So the vertex remains at the origin because H and K are both 0. For today, we're going to keep our graphs at the origin so you can get a better idea of how the A values come in. The negative will be a reflection over X in this case. So this is a reflection over the x-axis because the A is a negative and outside. And then the 1/2 will compress it. Meaning my graph will be wider than the original. So my original graph went through 1, 1. Being compressed by 1/2, it will go through 1, 1/2. So if you think about the fact that this absolute value is a piecewise, that really tells me that this graph is at 0 for x equals 0 because the graph was not transformed or moved. It tells me that the graph is negative 1/2 x for my x values that are going to be less than 0. And then it is 1/2 x, sorry, for my x values greater than 0 because it was reflected over the x-axis. So that reflection now changed my slopes, or if you think about dividing by a negative, it flips your inequalities. So as a piecewise, that negative is flipping the inequalities so that my slope is positive to the left of 0 and negative now to the right of 0 because of the reflection over that x-axis. So we're going down one, right one this way, and down one, up one that way. Because it is both compressed and reflected. Compression made it wider, the reflection flipped them from positive y's to negative y's. If you like tables, there is a table trick I'll show you on the next graph. So you can either rewrite them as piecewise or make a table. So this graph has a positive 4. That means it is stretched or more narrow. For today, all of your x's are going to be the same. So you can look at all of your x's at the origin, and then 2 to the left and 2 to the right. Remember that whatever it does to the right, it does to the left because it's symmetric. My vertex is also always at 0, 0 for right now. The a value multiplies the original y. So the original y's are always 2, 1, 1, 2 for the absolute value. So the a value multiplies to those points, giving you your new points. So if you like a table, the a value multiplies to those original points, which are always 2, 1, 0, 1, 2, and the negative 2, negative 1, 1, 2. Also create it as a piecewise and apply what we did yesterday. Yep.
Why do you have the YA at the top of your phone?
Because the y is for the black y value that never changes. The a is from the a value in the formula. So, yes. So the x and the y are always the same, and then you apply your transformations to them. So tomorrow we'll talk about changing and adding h and k with them. So again, if I make that same x, y, the negative 2, negative 1, 0, 1, 2, 2, 1, 0, 1, 2 never change. What you do is then apply the new rule. So in this case, the new rule is 1/4. So you would take 1/4 times all your y values. The downside to that is that some of them are tiny, tiny points. So if you understand this represents slope of a piecewise split at the opposite value, you can also plot it as slope. We know whatever it does to the right, it also does to the left. again, it's compressed or shrunk by a fourth. So like the table points right there, they're just much harder to grab. So